Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. Right, differentiate with respect to x. 4x squared minus 1 cubed. Okay, so this question looks a bit different because I've taken it off the pre-project maths papers. So 2012 was was the year where they did project maths with a small number of schools, and then everyone else in the country took the older type maths. So this is off the older type maths paper. The questions are still the same. The questions are still very relevant. So differentiate with respect to x, 4x squared minus 1 cubed. Okay. So y is equal to 4x squared minus 1 cubed. So it's a relatively straightforward chain rule. So take down the power, reduce the power by 1, and then you must multiply it by the inner function differentiated. So 2 4s are 8x. Okay, so yeah, why is it a chain? Well, can you see that the inside function 4x squared minus 1 in itself can be differentiated? So that's an inner function within the cubed function up here. Okay, so the easiest way then, because of BOMDAS, you don't interfere with this, because in BOMDAS you have to do O before you do M, you have to do order before you do multiply. So just tidy up the bits on the outside to give you 24x times 4x squared minus 1 squared. So BOMDAS will tell me I have to square that first before I can multiply it by the 24x. So that's your answer. Part 2, y was equal to the sine inverse of 2x over 3. So for this one, let's have a look at the sine inverse function. So sine inverse of x over a is equal to 1 over the square root of a squared minus x squared. Okay, so that's what we're using for this one. The sine inverse of x over a is equal to 1 over the square root of a squared minus x squared. Okay, so this is my x term, which is 2x, and this is my a. Okay, word of caution on this one, when they give you the rule, they assume a single x. Okay, if you have more than a single x here, then you'll be chaining. Okay, a bit like in the log tables where they give you a single cos x and you get minus sine x. But if you get cos 2x, for example, you're doing a little bit of a chain and you'd get minus 2 sine 2x. Okay, and I'll explain what I mean by that as I do this example. Okay, so dy dx then, or of course f dash of x, whatever you want to call it, is equal to 1 over the square root of my a is 3, so 3 squared, minus my x is 2x, all to be squared, but I must multiply it by the 2x differentiated. Okay, so it is 1 over the square root of 9 minus, so powers work square each bit inside the bracket. That's why the 2x all went into a bracket, to make sure that I remembered to square the 2 as well as the x. Okay, because very easy to put down 2x squared here if you had written above as minus 2x squared. Okay, so just watch out for that one. And of course it's multiplied by 2. So as in any fractions then, top by top. So my answer is 2 over 9 minus 4x squared. Okay, so that's part A done. Okay, so I'm just going to move part B then, C, onto a different page. Give us a bit of space. Okay. Differentiate root x with respect to x from first principles. So this was the hardest first principles question that I have seen being asked in Leaving Cert. So it hasn't been asked as part of project maths yet. Doesn't mean it can't be. Okay, so remember your first principles formula. The limit as h tends to 0 of f of x plus h minus f of x all over h, okay? And if that doesn't make sense to some people, there are videos explaining where this came from on YouTube. Okay, so to differentiate root x. So the first step is f of x. That's what you're given in the question. Next one, develop an expression for x plus h. So quite simply, x gets replaced by x plus h here. So replace all the x's with x plus h here. Okay, step 3, subtract them. Now, this is one of the cases and one of the few cases where it didn't make sense to write it as indices, I think, because I found that harder. So it was easier for this one to leave it as square roots. How do you know which way to do it? Well, sometimes it's trial and error. Sometimes you just have to try it both ways and see which way makes more sense. So probably when I did this first, I would probably have done it both ways. I normally do, just to see which one makes more sense. So I'm getting x plus h minus root x over h. Okay, and I can't really simplify it, I suppose, until I get rid of the square root signs. The easiest way to do it is to multiply it above and below by the conjugate of the top, because that will force all the intermediate terms to cancel. And I'll explain that as I do it. So what I'm going to do is I'm going to take this down here. So root x plus h minus root x over h, and I'm going to multiply above and below by what's called the conjugate of the bottom of the top. So like so. Okay, what am I doing? Okay, well, I'll show you why it's the plus version in a minute, but why multiplying above and below? So that number is 1. So 10 over 10 is 1. 3 over 3 is 1. X plus h plus root x over x plus h plus x is 1. Okay, and you know when you multiply anything by 1, you're not changing it. Okay, multiplying by 1 doesn't change the equation. So although it doesn't look like it, all I'm doing is multiplying it by 1. Now let me do it for you and show you why I'm doing it, okay? So just like any other complicated looking function, okay, it is this first one multiplied by everything in the second bracket minus this one by everyone in the second bracket, okay? Or like this if that's how you do brackets. Okay, so I'm going to write it out long and then I'll explain what's happening. So I'm going to get x plus h by x plus h. That's the first one, that one by that one. I'm now going to do this one by this. So I'll have minus, no, I won't, I'll have plus x plus h by root x. And then I'll have minus root x by x plus h plus minus root x by root x. So that's on the top. And on the bottom, I will have h times root x plus h plus root x. Okay, not too much I can do there. Okay, so the first thing is the intermediate ones cancel. Okay, that's why. That was the reason I multiplied it by the plus, because when you have two different signs here, you'll get the two terms here in the middle to cancel, a bit like the difference of two squares. Okay, so they cancelled. And the good news about these terms, when you multiply a root by a root, and you can try it on your calculator if you wish, root 3 by root 3 is the same as root 9, which is 3. Root 10 by root 10 is the same as root 100, which is 10. Okay, root 4 by root 4 is 4. Root x by root x is x. Okay, so there's a property there that when you multiply the square root of a number by itself, you get the number without the square root sign around it. Okay, so that is why I'm not too bothered about this term and this term, because I know now the square roots are gone. In that I'm just left with x plus h there, and at the end I have x, and it's all over h times x plus h plus root x. Okay, not too much I can do with the bottom. I have to live with the consequences of that because I introduced it there. Okay, so x minus x cancels on the top. So I'm left with just h over h times x plus h plus root x. Okay, no big deal if you had multiplied in the h up here. You would probably factor it out back down here again, because then you should see that h cancels with h there. That's, I suppose, why I've done this one before. That's why I didn't multiply it in up here. But if you had, don't worry about it. Just factor it out again, because you'll see h's all over the place, and they'll all cancel. So you're left then with 1 over, and be careful, that's 1 over. Just because I've nothing on the top doesn't mean the fraction disappears. Root x plus h plus root x. Okay, and then the last step is the limit as h tends to 0 of f of x plus h minus f of x over h. So that means let that gap between them approach 0. In fact, let it be too small, or so small that you sub in 0. So I get 1 over root x plus root x, because that h disappears, it goes to 0. So I have 1 over 2 root x. Okay, now just as an aside, and that's your full answer, just on an aside, okay, and I will always do this when I do a first principles question, if y equals root x, which in indices is x to the power of a half, let's do it by rule. Take down the power, reduce the power by 1. Okay, then using a reciprocal to bring that underneath the line by 1 over x to the power of a half. X to the power of a half is root x. You can see top by top, bottom by bottom, I do indeed get 1 over 2 root x. So I know that this is right. I'm happy enough because I got the same answer by rule. Okay, so that's f. That is differentiate root x from first principles. Okay, so like I said, the hardest one that I have come across is that one. So I think if you can do that one, you can do any one. Okay. Find the equation of the tangent to the curve y is equal to root x at the point 9, 3. Okay, find the equation of the tangent to the curve. So whatever curve that is, you have got to know that equation of tangent to the curve is slope. Okay, so whatever curve you get in a question, okay, all right. You can pick a point on it. okay? And the slope, the theory tells you that the slope of the curve at that point, sorry, now imagine that's a tangent and it's touching, okay? The slope of the tangent at that point on the curve, on the red curve, is the same as if you drew a tangent at that point with the slope, because remember, tangent just touches the curve at one point, so that line will have a particular slant or slope. So the slope of that tangent is the exact same as the slope of this curve at just that point. Okay, so that's why they often call it the equation of a tangent to the curve. Okay, because it's effectively the same thing, the equation of the curve at just that point, because the slope of the curve changes all the way. But at that particular point, it's the same as a tangent to that curve. In the same way, of course, I could draw a point at any place along that curve and draw a tangent to it. So whatever slope I get when I sub in that x value into dy dx of that curve, that is the exact same as the slope that I would get if I knew 2 points on that line and did y minus y1, or y2 minus y1. Okay, that's all the equation of a tangent to a curve is. And once you get your head around that, you're not really too intimidated then when they start talking about all these equations of tangents to curve. Okay, so you know that slope of that curve is equal to 1 over 2 root x. Okay, we know that because we got it in part 1. So it's in what is the equation of the tangent to the curve at the point 9, 3. Okay, so what is dy dx at the point 9, 3? Okay, well, that's xy. So you sub in the x value. So it is 1 over 2 root 9. And you know 2 root 9, or root 9 is 3. So it's 1 over 2 times 3. So it's a sixth. Okay, so the slope of the curve at the point 9, 3 is a sixth. Okay, and like any other equation of a tangent, because a tangent is just a line, we use that formula. Our point 93 is x1, y1, so y minus 3 is equal to 6 times x minus 9. Bring up your 6. 6y minus 18 is equal to x minus 9. Bring over the 18. 6y is equal to x minus 9 plus 18. 6y is equal to x plus 9. Okay, so the equation of the tangent to the curve at the point 93 is 6y is equal to x plus 9. Okay, so you can see it's the understanding of the question and what to do with that point 93 that's the hard part, not actually the maths themselves. Okay, so that's part B. You can see the older papers tended to have 6 questions on it, but much longer questions. So you've got 9 questions on your papers and somewhat shorter. Okay, let's try part C. Let f be the function. F of x is 8x plus sine 4x plus 4 sine 2x. Find f dash of x. Okay, well, it starts off okay. It's 8x. It's sine 4x. It's 4 sine 2x. Okay, so no product. It's never a product when we've got pluses and minuses in the middle. You just take each term and you differentiate them separately. Okay, so f dash of x, and I'm always have a close look to make sure that it's f dash and not f double dash. Differentiate 8x and you get 8. Differentiate sine 4x, so sine goes to cos. I get cos of the angle by differentiate the 4 plus 4. What does sine go to? Sine goes to cos again. Cos 2x by the 2. So f dash of x then is equal to 8 plus 4 cos 4x plus 8 cos 2x. Okay, so just like convention, we bring the numbers in front typically, and we put the trig functions towards the end. So no real difference between that line and that line. It's just, I suppose, written a bit neater. Okay, part 2, express f dash of x in terms of cos 2x. Okay, not the nicest of a question because it uses trig identities. Not something I hold dear to my heart. So basically it's saying write this function here in terms of 2x. Okay, so trig identities are here. So cos 2x is what it said. There's a cos 2x. There's a cos 2x. That has a cos 2x in it. Okay. Right. So which one makes sense? Okay. And it's why I don't like these questions, because it offers no guidance as to which one they want you to use. But typically, you try not to introduce other trig functions in it. So I've got cos 2x here. I wouldn't really be introducing sines and tans in that case if I'm hoping to write this in a different form. Okay, which is why I probably wouldn't use that one. And it's probably why I wouldn't use that one. So let's see, can we play with this one? Okay. So this is part 2 now. So f dash of x would still be equal to 8. Right, I need an expression for 4a. So let's play. So cos 2 squared of a is equal to a half plus a half cos 2a. So I'm trying to come up with an expression for cos 4x is what I'm going to do, but it'll be a for now, and then we can change the a's to x. Okay, don't really like the halves. Let's get rid of them. 2 cos squared a is equal to 1 plus cos 2a. Okay, let's bring across that 1. 2 cos squared of a minus 1 is equal to cos 2a. Then let's see, what do I do? I'm going to double the angle. So let's double the angle here. Okay, so let's put in our that work. Now let me see, I'm going to go back a line in case I confused it. So 2 cos squared, my angle is 4x, minus 1 is equal to cos 2x, sorry, is equal to cos of okay, so that looks okay. I have an expression for 4x. Okay, I let a be 2x, so therefore 2a was 4x. So I am getting 4 times 2 cos squared of 2x minus 1 plus 8 cos of 2x. So therefore I am getting then 8 plus 8 cos squared of 2x, just multiplying these in, minus 4 plus 8 cos 2x. Tidying the two numbers. So I'm getting 4 plus 8 cos squared of 2x plus 8 cos of 2x. Okay. So that's it written in terms of 2x. Okay, so I wouldn't beat yourself up too much if that's the part of this question, out of this entire question, that's the part that that doesn't, that you don't love. Some are good at it, some are just not. You can see it's trying to find the right identity that will allow you do what you're trying to do. Okay. Part 3. Prove that f of x is increasing for all of x. Okay, right. Prove that f of x is increasing for all of x. So increasing, decreasing functions. So the piece of theory you need to know is that f of x, the original function f of x, is increasing when slope is positive. And I think I have a diagram on the next page. I do. Okay. So the blue one is the original f of x, and f dash of x then is the red one. Okay. So what do I mean by that? F of x is increasing when the slope is positive. Okay. So you see all of this. Right. Well, let me explain. So f of x is slope. Okay. So you don't look at the trend of f of x, you look at the value of f of x. Okay, so all the way up here, my slope is positive. Okay, at this point, my slope is 0. Up here, I have a slope of what looks like 6. Down here, it's not very steep. I have what looks like a slope of 2. Okay, it doesn't matter that the trend of this is negative. Okay, this is values for slope. That's what f dash x is. Okay, so you're always looking to see, is your f dash x line above 0, which means it has a positive slope? Okay, or is it below 0, which means it has a negative slope? And that's that red line I'm talking about. Okay, where it is on the graph just gives you the value of slope. Right. Have a look at the blue line here. So while this is increasing all the way up to here, can you see that my red line sits above the x-axis? So it has a positive slope. Right here at the max turning point, my slope is 0. Then my original function starts to decrease. Okay, which means that the slope line is below 0. It's got negative values all the while here. Okay, until you hit the minimum turning point, and at that stage your slope is 0, and then you get this positive slope again. Okay, so it doesn't matter that I suppose it doesn't matter where the original curve sits. So even though that's a negative slope, I suppose this is a negative slope underneath the line. It's the very fact that it's falling, which means our red line here, our slope is below the graph. An important graph, takes a while to get your head around it. You need to be able to draw. So if I give you this cubic function here, the blue one, you should be able to somehow draw the red one above it. And just to give you a feel for that, if I draw a cubic equation as such, well, let me do that in a different color. Okay, can I draw the derivative? Okay, well, this is your first point. You know that your derivative is going to have a slope of 0 because it's a max turning point. You know here your slope is going to have your dy dx, your red curve is going to have a slope of 0 because it's a min turning point. Okay, between those 2 points, I know that my slope is negative, so my derivative comes below the line. I don't know how far it comes down here. I'm not putting any values here on the y-axis, but I do know that I get a negative slope. So all my y values, all my slope values are minus because the original function is falling, okay? And then I know up here, I get positive slopes, okay? Why? Because this curve here is increasing. Look, it doesn't matter that this original curve is below the line here. It matters, its slope matters. Okay, which is why this is above the line, it's got positive values of slope. So you need to be able to draw the trend of that dy dx curve as opposed to the values. So that's why back here I'm saying f of x, the original function, is increasing for as long as slope is positive. So this is telling me prove that f of x is increasing for all values of x. So what I need to prove is that you can never get a negative slope from dy dx. Okay. So let's take down our dy dx and let's see what that's all about. Okay, so dy dx we got to be 8 cos squared of 2x. I'll explain why in a minute. I'm writing it in slightly different order than I have here. Okay, why? Because you know what? This is a quadratic. I see a squared, I see a non-squared, and I see a number. Okay, remember that cos squared of 2x can be written like this. So pretend x in this case is cos of 2x, then don't I have 8x squared plus 8x plus 4. So I have a quadratic, albeit in a strange trig form. Okay, so hard enough to spot, but I suppose one of the easy ways of proving increasing functions is using the square root of b squared minus 4ac. And again, I'll explain that in a minute. So my a for this quadratic is 8, b is also 8, and c is 4. So let's put it into my minus b formula. So it is minus 8 plus or minus the square root of 8 squared minus 4 by 4 is 16, by 8 is 128, all over 2 8s are 16. Okay, I did that quite fast, and I did it because it's this bit that I care about. Okay, that bit tells me the nature of my roots. Okay, so I'm going to come over here and I'm just going to explain the theory here to the left. Okay, b squared minus 4ac, that number is always greater than 0 for real roots. B squared minus 4ac is always less than 0 for no real roots. B squared minus 4ac is equal to 0 for equal roots or one equal root. So this one here just means your quadratic sits on the x-axis, and that's how you get what's called equal roots. Okay, now I got a negative number when I did this. Can you see that? 64 minus 28 minus 128 is going to give me minus 8 plus or minus the square root of minus 64 all over 16. And I don't really care about the value minus 64. I just care that it's negative, which means my dy dx, or my slope, has no real roots. Now, I know you don't have complex numbers that chapter done, or you may not have them done, okay? But no real roots means that my quadratic never cuts through the x-axis. So it could float on the top as such, okay? But it never comes below the x-axis to give me these real roots that I talk about here, when x equals and x equals, okay? If you put the square root of a negative number into the calculator, you get a maths error, Okay, so there are no solutions, no real value solutions for x in that case. You can't solve it as it is, okay? And that is where the chapter complex numbers comes out of. That's why I'm mentioning complex numbers, but not overly relevant here. So if it never comes below the line, then it means I never have this red part here, which means I never have negative slope, which means my original function must always be increasing. So no real roots, therefore no negative slope, therefore f of x is, and you give them back their own words, is increasing for all values of x. So that's quite a hard question to get your head around at the start, but I suppose that's why I always know that this is a great way for explaining roots and the nature of curves, which is how I suppose how I spotted the fact that this could be a quadratic. Okay, and that concludes that particularly long exam question. If you've enjoyed this video, then why not join us in IT Sligo and use maths in practice. In conjunction with industry, we've designed an exciting new program in electronics and self-driving technologies, which uses cutting-edge techniques such as artificial intelligence, computer vision, and virtual and augmented reality. You'll need a H5 in maths to qualify. Check out the link below.